So let me also point out one thing. We noticed here that, so what we have for this affine vertex algebras, we always have a functor from a module of the horizontal subalgebra. Here, this very trivial two-dimensional commutative superalgebra to the affine one, and this is an exact functor, but it's not true. But an induced module of a simple module need not be simple. That sometimes happens. So this means if I start with a module that has a Löwe diagram of this type, then the induced module will automatically have a diagram of this type that satisfies all the properties of a Löwe diagram, except that the components need not be simple. Okay? So that's what it tells. So this means you learn a lot from the horizontal subalgebra. It gives you a structure, but you should never expect this to be the complete information. So with this in mind, I now want to discuss finite dimensional SL2. I think it's quite instructive. So, and I would expect that most of you learn something that you didn't know, right? You always expect about SL2, I do know everything. So let's first fix notation. So I call the generators E, F.
Okay, update. People can't see, can look at the screen.
Yeah. And they have the standard commutation relations. So you don't even need your glasses, right? Okay. Next one. But you know, I start. I get reminded to write large, and then it goes smaller and smaller again. Yeah, so maybe one of you can come forward and erase for me. You'll get a bonus point. So one thing I learned for teaching is that bonus points are a really good way to keep the students motivated. They always ask, do I get another bonus point? And so always homeworks give them bonus points. They like it. And
likewise, we give you bonus for writing big.
so what's the bonus? A piece of chocolate? Okay, good. Okay, so what other information do we need? One thing, let me write down, kappa stands for the Killing form. So what's the pairing of, actually I normalized it differently, I'm just seeing. Anyway, kappa is an invariant bilinear form on SL2. And we normalize it such that the pairing of E and F is 1, and the one of H is 2. What is the Killing form? What is an invariant bilinear form good for? I now immediately see I can fix a dual basis. The vector dual to H is 1/2 H. The vector dual to E is F. The vector dual to F is E. Also, so this means, and what does that tell me? That tells me that the Casimir is equal to, so I denote it by a C, is equal to the sum over the basis vectors times their dual vectors, E times F plus H times 1/2 H plus F times the dual vector. All right. And now let me write this in two different ways. Let me first maybe start with the H part, and then let me write it as in this way. What can I do is I have here the E times F, but I know the commutator E times F minus F times E is equal to H. So I can use this relation to write the Casimir in this form. This is now understood as acting on a representation. And similarly, I can write it using the commutator in the other direction. Then I don't get a plus h, but a minus h. And instead of a plus 2 times f times e, I get 2 times e times f. Okay. So I'm surely not telling you many new things. So now let's try to find modules. So what I want to reach with this lecture is, first of all, I build up basics for future lectures, but I also want to go to intertwining operators. So intertwining operators are operators that realize tensor product. Well, the tensor product here for SL2 modules is just given by co-multiplication. That's quite simple, but it's surely a good thing to start with that for finite dimensional SL2, and yeah. So anyway, this is what we are doing here. So let's discuss modules. What kind of modules do you know?
For what module?
For SL2. The Lie algebra SL2, we know it's realized by a traceless 2x2 matrices, so they act on two-dimensional vector space. All right, and that gives us the standard representation, the two-dimensional irreducible one, and then we know one more. I mean, we always know the trivial module. We also know a Lie algebra acts on itself, well, via the commutator. So it also has a three-dimensional irreducible module, the adjoint representation. And then if one works hard, not hard, but it's an explicit computation to verify that you get one simple module for each possible dimension. That's very special to SL2. Okay, so we have finite dimensional modules. And let me denote them by a row type sub n. So what is a module? It's a Lie algebra homomorphism into the endomorphism ring of a vector space. So here the n refers to the dimension of the vector space. Actually, the dimension is n plus 1, so the n will refer to the weight label. And so let's fix a basis to be v0 up to vn, and then and then we get a representation if we require that the endomorphism corresponding to H acts on each basis vector by a corresponding weight, by a corresponding eigenvalue. The E decreases the index by 1. And now I also have to tell you what happens if I take I to be 0. Well, I just define V negative 1 to be 0. So this means the vector V0 is a highest weight vector. It is annihilated by E, right? And it has highest weight n minus 0. It has highest weight n. So that's the label here. And then tell me if I'm too. This is too trivial. Well, anyway. And I decided to make this symmetric in F and E, as you see here. Here now I have to tell you that if this label is the highest possible label n, then I want F to annihilate it. So this means this Vn is the lowest weight module. So these finite dimensional modules are modules that have the property they are finite dimensional. The Cartan subalgebra acts semi-simply on it, and they have a highest weight vector V0, a lowest weight vector Vn, of highest weight n, of lowest weight n minus 2n of negative n, and you probably all have seen these modules before. Nothing new. Okay, next. What can we do to get more modules?
Just do the direct sum if you want.
Can you say?
Do the direct sum.
Can you say it again?
Direct sum.
Yes, I can do that. I can even take the direct sum of 3 of them. Now, any other idea except for direct sums? You can tensor them and you will get direct sums. We will see that in a moment. So how would I actually come up with these modules? If you give a Lie theory course, you would do the following. Let me start with a module generated by a single vector, V0. Give it the highest weight condition. That means it has highest weight, your favorite scalar, n. N is now not necessarily an integer yet. And make it a highest weight module by requiring that E annihilates 1, and then let F act freely. So that means it has then a vector v1, which you get by acting with f once, v2 by acting with f twice, etc. It clearly gives you an infinite dimensional module that has a highest weight. It would be a Wörmer model, yeah. Would you know how f acts on v1, for example? What does f do to v1? Right, v1 is so here in this case, how did I come up with this formula? How did I come up with the relation of these numbers?
I think it is because
You use the commutators, right?
I use the commutators. That's correct. I in fact use something else. I not only use the commutator. And I use something that's already on the board.
there.
No,
Yeah, it's there.
killing form.
No, not the killing form. Actually, it's here. I use the Casimir, right? Because what's the Casimir? It commutes with everything. That means it acts as a scalar on the module. But what does the Casimir act on a highest weight module? This is why I wrote down these formulas, right? On a highest weight module, this term annihilates the highest weight vector. This means on a highest weight module, it acts by some number purely determined by the highest weight. The highest weight squared over 2 plus the highest weight, right? But then I can, of course, use the action of the Casimir. It acts on every vector, so that it acts by the same scalar on v1, and so that v1 is and now I can use, but v1 involves just the weight of the corresponding vector together with the action of E times F. So I can deduce how it goes back, all right? So this means if I, and then I get this finite dimensional module by now analyzing which highest weight can I choose so that the Wörmer module has a non-trivial submodule, and it turns out it has a non-trivial submodule if and only if I started with a non-negative integer highest weight, and then take the quotient. So in particular, we now get more generally highest weight modules. Let's call them d plus lambda, so plus for highest weight. And what are these? They are now direct sum of, so they have a basis of vectors with index lambda minus 2e. So let me just write down how our generators of SL2 act on this. The index is just the weight of the vector. That means the eigenvalue under the action of H of the Cartan subalgebra generator. And now, and what is and now we define the action of F just to decrease the label by 2. So it's a little bit hard to make it symmetric. And now we do the exercise to compute what is the action of row E. So first of all, we require the highest weight condition that E annihilates the highest weight vector. And now let's think about how could possible row E, E act on a given weight vector. Well, we know that this given weight vector is the image of the vector of weight shifted by 2 under F. And now we can use the relation that we know that E times F is equal to the Casimir plus a polynomial in H. So that means that this is the action of the Casimir over 2. We get a minus 1 over 4 H times H plus H over 2 acting on this vector. And now we know how each of these elements act. So we get this is equal to lambda squared plus lambda squared over 4 plus lambda over 2 minus 1 over 4 lambda minus 2I plus 2 squared plus lambda minus 2I plus 2 divided by 2, whatever. It's not really important what this number is. The important thing is the highest weight is unique. The Casimir eigenvalue is uniquely determined by knowing that there is a highest weight vector. And now having the Casimir eigenvalue, we can determine the action of row E, right? Without this Casimir, I wouldn't know what to do, right? So this is important.
I guess when I get the highest weight and if the module is simple.
Absolutely, yeah. Here this module is defined to be the module generated by a vector, yeah. And in fact, a simple, it's important that it's indecomposable, right? It's generated by this vector. Okay. Now, as an exercise, you can similarly construct lowest weight mod.
I don't understand. Just the fact that the one you've written, how do you know the Casimir acts by a scalar?
Right. Why do I know this? Because the Casimir commutes with every element, and the module is generated by this vector. On this vector, the Casimir acts by a fixed scalar, and now I can, for example, look at this one. The Casimir action is the same. I can Casimir commutes with F, so that means the Casimir action on this vector and then this one is the same.
Because you assume it's generated by an eigenvector for H.
Exactly. Okay. Yeah. So it's eigenvector. So it's generated by a highest weight vector, right? And these two together fix the Casimir eigenvalue, and that fixes it. Absolutely. Exercise, do the same thing for lowest weight. You just interchange the role of F and E. That's just rewriting. Okay. Now, next thing we do what the physicists call a relaxed highest weight module, and one definitely has to relaxed highest weight module, and one definitely has to change the name. So we call it only a weight module. So if you because there is no highest weight vector, and then it's not a good name. That's it. Okay, next thing, we introduce a weight module. And I give it a superscript minus, and it and now it is as a vector space, it's just a vector space of countable dimension with a basis given by this v lambda plus 2n. And now I define an action of SL2 on it. The action of h, you can already guess, is just given by multiplication with the weight label. So as before, and now I have the freedom to define the action of E to just change the weight label by 2. That's consistent with the commutator of H. And now I need to define the action of F. So what can I possibly do? I can definitely do the same trick as before. So I wonder, I know that this v lambda plus 2n is, by the way I have introduced the action of E, the image under E of the vector within the weight label lambda plus 2n minus 2. All right. And now I can do exactly the same trick as before. I can replace f times E by the Casimir. So that means it becomes 1. I take a 1/2 out just because it appears everywhere. It's the Casimir minus 1/2 h minus h times this vector. But now I have a problem. I don't have, here I didn't introduce any highest or lowest weight vector, and I don't want to. I only want a weight module, no highest or lowest weight module. So this means this doesn't help me at all unless I put it as an assumption on this module that the Casimir acts by my favorite scalar, which is this delta. All right, so now I require that the Casimir on any v acts by multiplication with delta. If I impose this, then this again gives me a fixed scalar. Now I insert. You can do it. It will give a similar lengthy formula, and it fixes the action of f. So what do we learn here? And this is what I imagine is new to many, is that so we take a finite dimensional module uniquely fixed by the highest weight, which needs to be a non-negative integer. If we take a highest weight module uniquely fixed by choosing a complex number, a highest weight. A lowest weight module uniquely fixed by fixing a complex number, the lowest weight. Now a weight module fixed by choosing a weight, a complex number, and in addition a Casimir eigenvalue. So you have to choose 2 numbers, and it's not uniquely fixed, because if I replace lambda by lambda plus 2, I get, of course, the same module. Good, and these are the weight modules, and yeah, any questions? Right, but
We're going to consider E minus lambda comma delta the same as E minus lambda plus 2 comma delta. Is the way I understand?
yeah. So we observe that observation.
Yes, you might say they live in different ways. But
You see the way it is defined. The action of E just changes the index by 2. Right? That's independent of lambda. The action of H is just the weight label, and the action of F depends only on the weight label and on C, on the Casimir action. So in particular, we have this isomorphism. I can change it. Yes.
So I vaguely recall this highest weight business, something called category O or something, and that thing has some geometric description in terms of D modules microsploited somewhere.
Yeah.
Does this one have such a description?
Yeah. So The description that has some in terms of D modules is the category of highest weight modules. So not you don't need the finite dimensionality, and nobody has an idea about that. One would really like to understand more. Yeah, but no, nothing is known. Okay, so.
In other words, there's no geometric description of what you construct here.
Yes, not yet, and this is a really interesting question. There are definitely physics that have this type of. So maybe I'll say what happens in physics. So physics sometimes VOAs appear as invariants. As some kind of meaningful quantities of higher dimensional quantum field theories. And then also their modules appear, and it turns out these highest weight modules, they can be often nicely be associated to line operators. And this is in the business of so-called Argyris-Douglas theories. Whoever knows that, certain types of quantum field theories. These modules, the weight modules, I mean, they are affinizations, they appear in the context of surface operators. At least accordingly to Davide Gaiotto. That's what he explained to me. I don't think that's written anywhere. So, okay, why did I put a minus label here? I didn't treat E and F on an equal footing, right? And I decided for one direction doesn't have a coefficient, the other one has one. In particular, we see, the action of F decreases the label by -2 times a scalar, and the scalar is a polynomial in the weight label, right? Well, a polynomial can have a root, right? And whenever this has a root, then that means I get a 0. That means this vector becomes a lowest weight vector, right? So this means I have. So this means for generic choice of lambda, surely this polynomial will never have a root. That means there will never be a lowest weight vector. This module will always be a simple module. But if I chose it unwisely or coincidentally, such that for one of these infinitely many labels, I get a 0, then I have a lowest weight module as submodule. So this means let's write this down, and you can already formulate the exercise. So and the exercise will, of course, be to replace the minus by a plus. This means interchange the role of F and E, and then have the same conclusion, just that instead of a lowest weight module as a submodule, you will have a highest weight submodule. So we have this E minus lambda comma delta is simple unless we have a root. So this means unless this delta is equal to 1/2 mu squared plus mu for an element mu in the coset lambda plus 2z. And in that case, we have this module has a proper submodule. And lowest weight modules, I only introduced highest weight modules, but I told you exercise, do the same thing for lowest weight, and then you do the label -1. In this case, it has a lowest weight module of lowest weight, submodule of this lowest weight. So it satisfies this non-split short exact sequence, and then the quotient module will, of course, then have a highest weight module. Will be a and then and the exercise is to interchange in the above discussion the role of E and F. Well, something similar will happen, right? Okay. Let's see. Now, if we discuss the affine vertex algebra of SL2, what we will do is we will take every SL2 module of the finite dimension we can construct. So here I constructed an enormous amount of them for you and induce all of those to modules of the affine one. And then we will ask ourselves whether these are also modules of the simple quotient. And often enough, the answer will turn out to be yes. So this, in particular, the answer will be if this level k is chosen not to be an integer, so not the Westermino-Witten case, then all these mentioned types of modules will appear. So, right? And now we want to go to tensor products. So let.
So if you were to define category of weight modules more generally, you just allow arbitrary extension of positive to the highest weight and the lowest weight, that kind of thing?
Yes. Now, if we go away from SL2, one could ask, what do I impose? So first of all, did I impose any condition here? What do you think? I mean, did I write down the most general SL2 modules that are there? For sure, I did not. Because what did I impose? I imposed that the Cartan subalgebra H acts semi-simply. You can definitely drop that. I also imposed that the Casimir acts semi-simply. Right? And anyway, so in general, so it turns out things become quite problematic if you drop the condition that the Cartan subalgebra acts semi-simply. So this will be a requirement always imposed, but it seems to be okay to impose it. It turns out that the VOA tells you that the Casimir, or for higher rank, the central character, the center, has to act semi-simply, so that's not imposed. That comes from the VOA theory. But what is different already for SL3, so it might, I'm not sure at which rank it starts, but you could ask the following question. Given a simple Lie algebra, can I classify all simple modules that are weight modules in the sense that the Cartan subalgebra acts semi-simply? Maybe also the center. And for SL2, that's the answer.
Did you ask that each weight space finite dimension?
And that's the point. If you put in addition the condition that every weight space is finite dimensional, you can do it. SL2, it turns out, I don't have to impose it because every weight space is automatically finite dimensional. For higher rank, it turns out you have simple modules whose weight spaces are not finite dimensional, and it's enormously hard to classify. I think it's only done for SL3, but I'm not completely sure. It's enormously difficult, and in fact, it seems that VOAs, in fact, give constructions of these modules. So you use the affine vertex algebra to construct modules whose top level have infinite dimensional weight spaces for the Cartan subalgebra, and this gives constructions of these modules that otherwise are quite inaccessible. So we did this for SL3, and apparently that was from finite dimensional Lie theory already a quite pleasant thing. So upshot is already Lie theory of finite dimensional simple Lie algebras is more complicated than you think if you make your categories big. Okay.
For the rank 2 simple but not type A, I don't know, like that G2 right or
I think this infinite dimensional weight spaces happens for all simple Lie algebras except SL2, if I remember.
Except SL, okay.
So it doesn't happen only for rank 1. I'm pretty sure. Okay, tensor product. So so I'm required to stop at 4 sharp, and I will manage. So we'll only quickly discuss tensor products. So what do we do? We have two representations, rho and rho primes, and then you define the tensor product. You call it rho times rho prime. It's now just acting on the tensor product of the underlying vector spaces. And you define it by saying that that for any element of SL2, so for x as any element in SL2, it acts as first by x on the first vector, and then by x on the second vector. So we say it has trivial co-multiplication. And then with this formula, it is with this formula, it is not hard at all to compute a few tensor products explicitly. So namely, if you take 2 finite dimensional representations, the one of highest weight n and of highest weight m, then you get a direct sum of simple ones, and the weight label starts by highest weight absolute value of n minus m and goes up in steps by 2 up to highest weight n plus m. Right? So this module is not hard to find because you just take the tensor product of the highest weight vectors, then this one annihilates it, this one annihilates it, so it's again a highest weight vector, and via this formula the highest weight adds up. So this means you get immediately that such a highest weight module appears as a submodule. If you then know that the category of finite dimensional modules, weight modules, is completely reducible, you know it's a direct summand, so you can subtract its character, and then you see that there's a unique vector of maximal weight still, so it must be a highest weight vector. It corresponds to the next summand you iterate. You immediately get this formula inductively. So this is a very quick thing. What about rho n tensor product with a highest weight module? Well, you can do the same exercise and yeah, you get a finite sum of highest weight modules. A similar formula holds for lowest weight modules. Next thing is you can, for example, take the tensor product of 2 highest weight modules, and what you'll get is you get you get highest weight modules, but in this case this goes up to, I mean, it doesn't truncate, so you get an infinite sum of highest weight module. So what you see here is already, well, the tensor product of 2 highest weight modules is nice, but it's not in the category in the strict sense, in that it's not a finite direct sum. You would say it's in a completion that allows for infinite direct sums. But what about a highest weight module times a lowest weight module? So, and, by the way, why can you compute it? Because you can find successive highest weight vectors here, right? And this is now here the difference. In this one, this module has highest weight vectors, this has lowest weight vectors. In the tensor product, you don't have any room anymore to find highest or lowest weight vectors. And that makes it, so that means this one here is already, you don't know how to compute it. And even worth any module times an E-type module, for example, an E minus lambda comma delta. In particular, if you take M and E-type module as well, well, you have a big problem because not only you can't find highest weight vectors, you already can't find it here, but you also don't even have any room to diagonalize the Casimir. Right? So you are not able to specify how does
I don't understand. Casimir is diagonalized there, take a diagonal basis. Casimir is diagonalized there, take diagonal basis. Tensor product of diagonal basis.
Yeah, no, because what's the co-multiplication of the Casimir? The Casimir is a polynomial, right? So this means a row of row. So no? Very good point. So this is definitely. So you get what you are saying. That's but then you get a plus mixed terms. And you have no room to control those mixed terms. Right? You get a term of type rho E times rho prime F. And you have no truncation condition that gives you a way how to diagonalize it.
Whatever you have left commutes with all the actions of the algebra, but you have no idea what it is. That's
Exactly. And you can play around. You just don't have a way to specify. You can't diagonalize the delta. So this means you have to.
Mod out by terms. Can you mod the mixed terms? Can you somehow divide out by that?
I think so the way to think about it is this is a huge thing, but it should allow for quotients that are these E-types modules. That's what you. But so let me put it this way. I mean I don't want to treat those, but I also haven't found anything ever treating these tensor products in the literature for a reason, because you just don't know how to treat it. And the miracle that we will partially see, so there is of course no hope that this should become better for the vertex algebra, right? Because the vertex algebra is the affinization, and the lesson is that of course if you affinize, things become more complicated. And but the interesting thing is the condition to define a tensor product for the vertex algebra is so severe that it truncates enormously. And it will turn out that there exists, even though on these SL2 E-type modules there does not exist a good tensor category structure, on the vertex algebra there will be. So all of a sudden the vertex algebra realizes something that already finite dimensional SL2 can't. That's kind of pretty.
I didn't understand what you just said.
It's an outlook for the coming lectures. So if you have to hurry because of rain, it will start soon. But I want to give the outlook. So what I wanted to have, so the aim of this lecture was to simply recall a lot about SL2 that you probably didn't know. Right? In particular, I introduced all these infinite dimensional modules. And I wanted to convince you that already for finite dimensional SL2, tensor products of these infinite dimensional modules are a complicated thing. Something in particular, the tensor product of two modules is only well defined if you go to completions. I didn't discuss completions, but that's a necessity for it, definitely. Okay, and so the plan is next lecture I will write down the definition of an intertwining operator. That will be 50 minutes. A little shorter, and then I want to give you some idea how they relate to tensor products.